Now, let's take the front door. So this is the door to the front passenger seat. And let's estimate the surface area as, who knows, 1 square meter, right? So now here's what we're going to do. Let's say we're traveling at 100 meters per second is unsafe. So how about 50 meters per second? This car door is 1 meter by 1 meter. I know that's unrealistic, but who knows? So let's see how much pressure is being applied to this door as the car drives by.
Is it a physics problem or math problem?
It's actually a physics problem. So assuming it's not a windy day and there's turbulent flow everywhere, how can we determine the force on this car door right here? Well, first, let's calculate the Reynolds number of this guy right here.
Is this actually fluid dynamics?
Yes. Given the value 0.0013 grams per milliliter, so to convert that to kilograms per cubic meter, this is moving at 50 meters per second. The characteristic length times 10 to the negative 5 pascals per square meter. And yes, believe it or not, this works the exact same way as just saying newtons per square meter. Wait, pascals is pressure. I don't know why I put newtons. No. Yeah. Okay. So, what does this officially give you for the Reynolds number, which is unitless? Well, this gives you, why does it not put it in? Wow, lots of fascinating choices being made today. 3.6 times 10 to the 6. Now, what does this number actually tell you? Well, the Reynolds number is the ratio of inertial forces to viscous forces. If it's inertial, we know that it's regular pressure doing all the work, and we can just use the blanket Bernoulli equation. If it's viscous, then things get a lot more complicated as we have to get into actual difficult fluid dynamics. But since the ratio is high, that means that inertial forces take over, and we're happy, totally happy, with just mindlessly plugging in Bernoulli's equation, which is approximately that half times the magnitude of the flow velocity squared is equal to, you just get that the pressure is approximately half times the density times the flow velocity squared in cases where the inertial force dominates. So all you have to do is plug this in and get, in our example, the density of air is 1.3 kilograms per cubic meter, and well, the velocity squared is 50 squared, which gives us 1.3 times 1250, which is just 1625. So now just divide this by the area and you get a representation. This is approximately the force on the car door. Now in cases where the Reynolds number is low, you actually do the exact same thing, but instead what you do is you take the inertial force, which is probably very low, and then all you have to do is divide it by the Reynolds number, which is also probably very low, and you'll get the viscous force, which is the truly dominant force. In this case, you can actually, well, do the exact same thing for F inertia, just saying F inertia is equal to F viscous times the Reynolds number. So then you can calculate F viscous via the very same method. So if you actually want to go through and calculate the total force, it's going to be that 1625 number plus 1625 divided by 3.6 times 10 to the 6, which just gives us okay, well, yeah, it's not a very big number. 1625.005. So you can see the dominance of the inertial force as compared to the viscous force. Now, when you're on the scale of cells and bacteria, for example, then when you're swimming through cytoplasm, which is a much higher viscosity material than air, for example, and you're working on very low lengths, like for example, a cell nucleus might be 10 micrometers long instead of 1 meter long, then the Reynolds number is going to become very low, since this is going to stay around normal values while this is going to shrink immensely, which means that viscous forces are going to dominate over inertial forces, which makes sense. We're on the cell level. Inertial forces aren't really going to stop anything because they're dependent on mass and size more than anything.